Previous video we have shown how one-dimensional patterns can be used in an across-subject analysis when all subjects measure the same attribute. In this video we will show how multidimensional patterns, so two or higher dimensional, can be used in an across-subject analysis when the subjects do not measure a single attribute but a number of attributes. So we will use an example from our own research in which subjects rated a number of aspects of processed images. So there were 16 images in total, and two subjects rated for each image 4 times the amount of blur. Then they also rated the amount of noisiness in the images, and they rated the overall quality of the images. So there are 6 matrices in total, 3 attributes times 2 subjects. The images themselves, the 16 images, were created by varying 2 aspects of the images: the amount of blur expressed in the first number and the amount of noisiness expressed in the second number. Now we've read all this information into ILLMO. That means we have 6 attributes, and we have one two-dimensional pattern that consists of 2 one-dimensional patterns. So the first pattern expresses the amount of blur, which is, or the second, this is the amount of noise. The first pattern expresses the amount of blur, and if you combine them, you get 16 combinations of these 2 factors. Now we can use this pattern to perform multiple regression. So we connect to this for the first group of measurements, the second group of measurements, for the third group of measurements, just to check what we have done. So we see that now all attributes are connected to the same pattern, and we can, for instance, look at the regression coefficients, the first regression coefficient and the second regression coefficient. Now, a visual way of showing the same information is when we go to the stimulus space. We see that the first 2 vectors express the direction in which perceived blur increases, the third and fourth in which perceived noisiness increases, and the 5th and 6th in which direction in which the quality increases. Now we can see that some of the vectors, at least for the attributes blur and noisiness, actually are pretty close together. So we might turn these into group vectors by saying I'm going to a polar system, I'm going to make the angle into a group variable. Let's see if I'm doing it. Yeah. And the same thing for the other group. Go to polar coordinates and making it into group vector. The way this shows up is that now these 2 vectors are overlapping. And that gives a small decrease in the AIC, so this is a somewhat better model, not surprisingly. Now in this case the pattern is equal to the pattern that we've entered. We could also say maybe we make this pattern as a variable. Now a pattern in 2 dimensions needs to have 3 fixed stimuli, and we might want to put them at 1, maybe the extreme one here is 12, and then the extreme one in the other cases 4, and make the other points make them variable, which is the same thing as what is normally denoted as multidimensional scaling in the statistical literature. So we can optimize this pattern. It takes a while because it's quite an extensive process. And we see that that indeed improves the performance. despite the fact that the configuration becomes somewhat, oh, I should have done 13. So we can reset the ND pattern, and so change this to 13, and then form this again.